Hello, everyone. Welcome to another session of the DataHour series. We will be starting shortly. Stay tuned.
Hello.
Yeah, hi, Vizal. I'm really delighted you have joined us. We will be starting shortly. We'll wait for others to join as well.
Okay, great.
Yeah. Hello, everyone. Welcome to another session of the series. We will start this session at 7 p.m. IST, and soon I will be sharing two polls. So make sure everyone to participate in this. Till then, let's get to know each other in the chat section. You can start from your location. Okay, so guys, I'm shooting two polls here. First one is regarding your location, and the other one is to know your experience level in this field. So, which I expect everyone to engage with. Okay, sir, I guess we can wait for 2 minutes more so that we have a large number of audience so that we are good to go. Okay, so everyone, good morning, good afternoon, and good evening, respective of the locations you are joining us. As we have participants all across the world, welcome to another session in the Data Hour series. We are thrilled to have you this evening for an interactive learning session. I, Rakshana Beriya, part of the data science team at Analytics Vidhya, will be the moderator for this session. For those who have joined us for the first time, a brief introduction about the Data Hour sessions. With the intent to make learning data science more engaging to the community, we began with our new initiative, DataHour. DataHour is a series of webinars led by top industry experts where they teach and democratize data science knowledge. Now on to our session today, which is making sense of clinical text data at scale with NLP. Despite ongoing efforts towards using natural language processing in information extraction from electronic health records, natural language processing has repeatedly demonstrated its feasibility to unlock evidence buried in clinical narratives. In this data, Vessel is going to demonstrate how machine learning can facilitate rapid development of NLP tools by leveraging large amounts of clinical text data. So before we kick things off and I introduce the session presenter, a quick recap of the housekeeping items. We are recording the session and we'll make the recording available in a few days on our YouTube channel. Please use the Q&A section for asking any questions you might have during the session. As the data hour progresses towards the end, we will do our best to answer them. Also, we will share a feedback poll towards the end of the session, which I request everyone to participate in. Now, on to our speaker in this session of Data. We have Vessel Kochaman with us. Vessel is a well-known thought leader in healthcare NLP and works as a lead data scientist and ML engineer at John Snow Labs, improving the Spark NLP for Healthcare library and delivering hands-on projects in healthcare and life science. He is also pursuing his PhD in ML at Leiden University, Netherlands. Wessel has a broad consulting experience in statistics, data science, software architecture, MLOps, machine learning, and AI to several startups, boot camps, and companies around the globe. He is also a Google developer expert in ML, recognized by Google officially. Over to you, Wessel. The virtual stage is all yours.
Hello, everyone. Is that okay right now? I just dropped and then got back. Is everything good right now?
Yes, sir. We are good to go. We can start the session now.
Okay. Sorry. Last minute Murphy just happened, so I was kicked out. So I hope you all can see my screen. This is Veysel from Johnson Alders. I'm the head of data science, leading a healthcare and NLP team over there for the last 3 years. Yeah, I'm really glad to be here with you guys. So if you don't know what we are going to talk today, but briefly, we are trying to explain how we can make sense out of clinical text data by using certain libraries and models. And then I personally have been working with in this domain for the last 5 years. So I work more than 100 maybe clinical projects, clinical NLP projects mostly. working with the other like pharmaceutical and the large healthcare companies like Roche, Novartis, and then the large hospital chains like Kaiser Permanente. So I will try to color my talk with this kind of stories, and I will try to explain why we need certain components, why we need certain models to solve certain problems in healthcare. That is why whenever I talk about these issues, I always change the topic. I always change the story is by adding new experiences from my latest project. So let's start what we are doing in healthcare domain with NLP, how to solve NLP problem, how to solve healthcare problems at scale with NLP. Looks like I'm not able to move. Let me try again. Yes. So like as you can see in the abstract of my talk, right now there are some unacceptable trade-off between the delivering state-of-the-art accuracy in healthcare, and then we also have a big problem generalizing over unseen data points. This is highly a crucial issue, as you know, as it's in every machine learning domain, by the way. This is not just for healthcare, but in healthcare, there are some intricacies that I'm going to focus more on today, especially the preventing the sharing of the protected health information, as well as the challenges we face today in healthcare text data. Okay, so we try to find a sweet spot between all these challenges to deliver what we need to solve that certain problems. Of course, you are all familiar with the type of the data that we deal with, right? As far as I see from the poll at the beginning of this webinar, I saw that most of you have up to 3 years of experience, as far as I see. So you may already be familiar with the structured data, of course, during the Kaggle or some other competition or some bootcamp related data sets, right? Then our main job was to convert this unstructured data into a structured way so that we can start analyzing, we can start exploring the data and then build the model on top of this. But when it comes to healthcare data, we are at whole another level actually, because the healthcare data is not designed for operational purposes. Actually, this is designed for the operational purpose of the efficient management of the hospital, but not for analyzing the data for the other problems, right? So when it comes to healthcare data, there are some nuances. The language is fuzzy, contextual. There are so many abbreviation, acronyms, jargons that we may not be familiar with, even if we speak this language as our as a native speaker, we may never be able to understand what is being discussed, because the goal is, as you can see from the certain documentaries or read from the papers, usually more than half of the time that the physicians or the healthcare providers spend their time on the record keeping. So that's why the major advantage of using NLP or machine learning approaches in healthcare domain is automating the record keeping process. So to reduce this burden, to reduce the time that is spent on the record keeping, will help the care providers to spend more time with the patients and to solve the real world problems by using their own findings, own judgments, own experiences, right? So that is why they are developing some skill sets. Even during their medical education, they develop some skills inherently that they try to be fast while keeping the records. So they don't worry about if they are going to use this text data later on for the other purpose. Of course, there are some digitization effort, especially in the electronic health record domain. But when it comes to text data that is scribbled by the physicians or the nurses are still high. And then there are many startups or many tools that are trying to leverage the information hidden inside these notes, right? Because if you are admitted to a clinic, there are some reports filled by the nurse or some physicians. And then after your visit to the clinic the next day, you generate some notes as well. So across multiple visits to the hospital, you generate hundreds of notes, maybe sometimes. If you have a chronic illnesses and then you keep visiting the different clinics across the country, you probably have more than 1,000 records, and then half of them, maybe more than half of it, is coming from the free text. So that's why if you read this as a normal human being, even without using machine learning, you still have a problem because of the missing context, lack of experience in the terminology being used, or the vocabulary, or some automation tools, right? That is why the one chunk, one sentence would mean different given the context. So that's why the natural language processing algorithms and then the models needs to be fine-tuned on this specific domain. So we can say that healthcare NLP, as it is the case for all the other domain, by the way, when it comes to NLP, is an uber domain specific field that requires downstream fine-tuning. So how everything starts in healthcare NLP? As I mentioned before, the systems used to generate health data at hospitals are designed for operations. Operations means that to better to take care of the patients in a better way, right? It's not designed for research or analytics, because that is understandable, of course, because they need to take care of the patients or increase their efficiency as much as possible when it comes to patient health. But when we try to extract knowledge from this text data, we usually fail to do this. It is not an easy job compared to all the other domains, especially in the other. Even the tweets are much better than compared to healthcare data, because you can generalize over the tweets and you can find the data, even unlabeled data, as you know, due to the transformers, right? Even the unlabeled data would be really helpful to fine-tune the models. But when it comes to healthcare data, the data is not open as well. So there is a shortage of open source text data in healthcare. And even if you have it, they are usually de-identified, and then they are usually because of the identification and then the obfuscation, like replacing the sensitive information with the fake data, the consistency is ruined. Sometimes it's not as useful as it could be if there is no de-identification applied. So everything starts with the unstructured electronic health record, EHR, we say that. Then we extract the information and then create a common format. There are some common formats in the healthcare analytics, like H7, FIR, etc., so that you can extract these kind of entities, like drug names, medication names, disease names, condition names, procedure names, and put in a common format so that the other downstream data analytics tool can consume this, right? So this is the first step usually. So the NLP comes into play with this stage a lot, by the way, because we need to understand the text and then extract these information by the tools that I'm going to explain today. And then when you have this common format, the next step is usually putting these clinical facts on a timeline so that you can build a longitudinal view of a patient, right? Because one clinical facts would mean different given the timeline or given the history of the patient. So you need to put all these clinical facts on a timeline per patient to draw a longitudinal view. And then you would be able to answer the questions by using this data. Like what kind of questions? What is the probability of having a metastasis from one organ to another? Or what are the opportunities to intervene in during this procedures, right? Or what parts of a patient's past history would be reviewed? As long as you understand, you explore everything from a text data, you would be able to understand well, you would be able to understand the relevant information and then use this information as a feature. Because NLP is not just there to extract information, it's also there for feature engineering step that you are going to probably need to build some downstream deep learning or machine learning models. So putting the clinical facts on a timeline means that, let's say, as I gave an example before, let's say that you have a chronic illness, you visit the clinics for the last 5 years. So each visit would generate a note. If we somehow manage to put all these clinical facts on a timeline, right? Like just pick one patient, pick all the records belonging to that patient, and then try to put all these documents on a timeline. And then not just the documents, but the facts that are mentioned in the text data. It says that the patient visited us 3 months ago, and then diagnosed, blah blah, right? So you should be able to understand that 3 months ago, that referential date information given the today's date, and then put this onto on a timeline. And you should also link everything together to create some knowledge graph so that you can query the text data as if it's a structured data. If we can manage this at the end of the day, we should be good to go for the downstream analytical test, right? So what you see on the screen right now is the ideal condition, actually. Like this one sentence, just with one sentence, what if we would be able to extract all these information, right? By using all the tools, pre-trained models, or new models that we are going to need to train again, right? The ideal situation would be, of course, you may not need to extract all this information if you are just dealing with the, let's say that diabetes related entities. You can just focus more on this part, but we usually even need the minimal chunk of information that we might need, because if we are going to use this as a metadata, right? Because let's say that we have one text data. Now we build a model, we just fit this into another network, and then let's say that we just build a text classifier, right? But if you don't have a metadata attached to this document, you can still extract metadata from the document. It's like the gender of a patient that this not belongs to, the age of a patient, or let's say that there are some medical terminologies like RX norm, ICD-10, etc., so that it could explain more than what you can see, because there are some hierarchical relationship between the terminologies. So it can be just one single text, but if you can extract this kind of information, that is usually the combination of years of experience for a well-trained nurse or physician or a healthcare analytic or healthcare analyst, right? So you would inject so much information into your pipeline rather than just extracting information. So for this test, for example, I extract the dosage and then the drug, and then find the relationship between dosage and drug, and then I send it to the RX norm resolution model, and it returns its RX norm code. And I also ask NDC resolver, what are these terms? I'm going to share a notebook with you, by the way, at the end of this session, like a collab notebook, so that you guys can also check what those means. During this webinar, I'm trying to stick to the Spark NLP for Healthcare library, which I'm leading for the last 3 years. So to build all these models out of the box, which you can try free as a free trial. So, and I will try to explain how we built the concepts so that you can solve the problems at scale. Because the pipeline that you extract these entities, these relationships on one single sentence, may not need to change when you try to do the same for 1 million records. That's why I call it scale at scale, right? So if you build a pipeline to extract everything that you see on the screen right now, you can just ship your code into a cluster and then extract information from 1 million records with the same accuracy. Of course, given the number of the nodes and then the size of the like a computational resource. So of course, you will like the time will change. But the ideal situation is to be able to extract the entities, assertion status, which is the negativity scope, and then the terminology codes, SNOMED, ICD-10, UMLS, etc., clinical entities, and then the relationship between the entities. Okay, so that's why we built such a let's say that I like to explain the concepts in such a diagram, actually, because everything starts with the clinical entity recognition models, because it is the minimal meaningful chunk that you can extract from any text. So because it's a plain text, you have no idea what it has, but as long as you have the entities, you can only have some basic statistic like number of the tokens, or you can have some lookup lists or some regex, and then you can still extract the entities. But if you are going to do this over 1 million records, there will be so many gaps that you may need to close, and then you would need many different type of models given the problem that you are trying to solve. Like, of course, always you need to go ahead and then check your task. If you are trying to solve problem A, you need to go back and then try to build the pipelines and then use the models and then the submodules to let you achieve that goal. Okay, so that's why you cannot just start with open-ended and then try to see what you can. Of course, there are some exploratory analysis. If you don't have any task at hand, you can explore your text just by using the NER models. But if you are trying to solve some problems, which I'm going to explain one text, by the way, like one use case during this study, and then I will try to explain how you are going to use NLP to solve that specific problem. So everything starts with NER, name identity recognition, to extract the text. And then the relationship between the text is relation extraction, right? So the admitted is a, for example, admitted for nausea due to chemo. So we have a treatment entity, we have an occurrence entity, we have a symptom. So, but we need to find the relationship between what happens before and after. Or we have a 40 units of insulin. So we have a drug and dosage, but we need to connect, there might be multiple dosage in the same sentence. So we need to connect the dosage to the drug so that we can create a new chunk, like a longer span, to feed into some other downstream text. So some other downstream text would be like a clinical entity linking. So this one is, as I mentioned before, there are some medical terminologies. Since most of you may not be familiar with these terms, let's call it some medical terminologies like SNOMED, ARISNOM for extract, like assigning a drug codes for the drugs in market, and ICD-10 is for the clinical conditions, CPT for the clinical procedures. These kind of codes are highly useful to let you fill some forms when there is a certain treatment applied in a hospital, so that the hospital could send these forms to some insurance agencies for the reimbursement purposes. Or you may want to do some analysis with the ICD-10 codes because it's hierarchic, right? So that you can understand what kind of diseases or conditions or emergencies happens over the weekend on a certain period of time by using this hierarchy between the events. I see some people raise their hands, but I will try to explain or answer the question but at the end of the webinar if I can. If I need to answer right now, please ping me, like the moderator could ping me right now, but otherwise I plan to answer all these questions at the end of the session. So the next one is assertion status. Assertion statuses you might have, by the way, I'm going to explain each concept one by one by going back and forth between the notebooks, okay? But briefly explaining, assertion status is the negativity scope of the entities detected at this stage. And the identification is detecting sensitive information. Right now, in this example, it is dosage, but in this example, there are some patient name and age and profession that needs to be masked, right? Or replaced by fake entities if you are going to exchange share some patient data with another care provider or within the hospital. You need to abide by some rules like HIPAA or GDPR, right? So you need to detect the entities which NER is needed over there, and then apply some logic to mask or obfuscate. So clinical name identity recognition is not just there to highlight the entities, as I mentioned before. So the first goal would be like extracting structured data from free text, because given the subdomain, given the problem at hand, you may need to use hundreds of different name identity recognition models. For example, this one is pathology NER. Pathology means medication, by the way. So extract 7 different medication related entities. So this one is anatomy NER. It extracts different part of the bodies as under different classes. So organism subdivision, organ, pathological formation, these kind of things. So there is no way that you can extract, right? You can use one model and can extract everything. We try to do this, by the way. We have one major model which you can extract more than 80 different entities at a time. But we even with that major giant model, we still use all these sub-modules to increase the coverage, to close the gap on some domains that we haven't seen before. So that's why, because name identity recognition is a token classification problem, because we basically, the model tried to assign a label for each word, each token that you see on the screen right now. And then by assigning these labels, we use some deep learning architectures, which I'm going to explain today. So that what makes this one capsule, like the capsule is a form, one is a dosage, etc. What makes this one capsule is a like one capsule of Advil for 5 days? Because we need the entire phrase sometimes. Like give me all the drugs and then the let's say that give me all the drugs and then the form for a patient, right? If I ask this question and then answer this one, I need to find all these entities and then find the relationships and then define the span. Maybe I'm going to use that phrase in some other task. Maybe I'm going to get the sentence embedding of that phrase and then use this for another like a similarity task, right? So the first goal is extract structured data to fill up some forms or to fill up some, to create some intermediate common format structured data. The second one is automate record keeping and abstraction process, like to reduce the time spent on record keeping. There are some repetitive tasks. Anything that is done more than once can be automated, by the way. So by using this kind of like how human being decide, like how human being connected us in his mind, we can, if we can find this pattern, we can automate this process as well. So that's why we try to, we like one of the most important benefit of NLP in healthcare is automate record keeping. And by the way, as I mentioned before, maybe 80% of the time it's a copy paste in the healthcare settings. So when a physician starts to fill up some form, most of the time they start with some template and then fill the blanks. So that's why there are, and even their medical training, they like the physicians are trained to do this process as much as like as fast as possible. So that's why this is bad and good actually. Bad, which means that there is no much, you know, there is no like, because of the like it's hard to separate the issues and then the domains if you are always using a certain templates for the models. But for the machine learning perspective, it is, of course, it is good. Why? Because it's easy to find the generalized model. Even 2 doctors or 3 doctors do not usually agree on each other. And then we sometimes annotate, we work with the physician annotators who are annotating all these data sets to train a model. Even some, like the model is trying to find a pattern across all these annotators. That's why the annotators, like the half of the errors usually comes from the annotation errors, as far as we see for the last 5 years. And then the third one is feeding downstream tasks. Downstream tasks are maybe you are going to build some deep learning model and you need some features, or you are going to build some random forest classifier and then you need some features apart from everything that you already have. So you can extract these features, entities, and then assertion statuses, relationships, positive and negative relations, etc., and then use this as a feature. Okay. So one example. I'm going to show some code as well, by the way. I'm just trying to give some high-level overview in the first 15 minutes, and then I will jump into how we accomplish this. Because everything that you see, this is not a black magic. Actually, you can do the same. You can just run the notebook, and then you will end up with the same, like a similar results. Of course, on your text, it might like the results might change because of the nature of the machine learning. When like one of the biggest problem that we NLP engineers usually face, or machine learning practitioners usually face, when we try to communicate these findings or these results to the customers or the stakeholders or the managers who may not be familiar with the concepts, they always try to treat this, you know, it's like a software development purposes. So we need to have like 90% accuracy. We need to have this, and no, you cannot guarantee this. It always depends. People hate this answer, of course, when I say it depends, but it's usually the case that we need to see their text data. Due to this PHI issues, protected health information, you may not believe, but sometimes we even need to work on a data without seeing the data. Like we work on some projects with the customers with their own data, but we are not allowed to see their data sometimes. There are some strict rules on their end, but they still want to solve their problem. So we sometimes generate fake data to build the pipeline, and then ask them if this fake data is similar, or the customer generates some, like the project owner generate some fake data and then share with us so that we make some estimates. Like it's really hard doing a data science without seeing the data. Actually, it's really disturbing. But sometimes I remember a project that I had to create a test and train split without even seeing the data. Because without seeing the data, how you can create a test split that you don't shoot in your foot, right? Because at the end of the project, you are going to be evaluated with the test data that you splitted at the beginning. But if you had to do this at the beginning without seeing the data, you need to do some black magic to do the split, finding the representation. So the most common way to do this, what I usually do is I throw everything that I have in my arsenal, right? So I use maybe more than 50 different NER models to extract all the entities and then extract some metadata from the text data without seeing that, by the way. I'm just able to see the numbers, not the chunks itself, but I know the type of the chunks. So I use this information as a metadata to do the split, proper split. So let's not talk about this, but talk about in a situation that you have the data, you can see and you can make sense as a human. So this is the case, predicting if a patient would develop a metastasis on a certain sites. So there are patients, some lung cancer patients, let's say, who have been visiting the clinics for the last 5 years. And then there are some metastatic metastasis happened and then spreading from one site, one body part to another. So over the course of a 5-year trajectory, so there are probably more than like 500 different documents generated so far. Yeah, I saw this, and then I can say that there are sometimes we see more than 1,000 documents per patient over 5 years. So the goal was analyzing all these PDF documents, all this text data. What if we can find a pattern, to extract, if we can find a pattern between the patients to understand what makes cancer spread from one organ to another. This is highly clinical, like a clinical use case, right? Highly important use case. But NLP plays a role here without even using any scalar data. If you can extract all this relevant information, given the task, we devise the entities that we need to extract, because you need to find the entities given the case. You cannot just throw, of course, you can throw all the NER models that you have, but it is not going to replace the fact that if you can extract the entities, that would be highly useful for your own use case. Because to answer this question, we need the stage information, we need the cancer type, we need the body part, we need some assertion statuses like it happened or not, it will happen in the future, or it has already happened in the past. These kind of assertion statuses, and you need to find the relationship between the diagnosis and then the body part, like a maths on brain. As you see, maths is it's not metastasis, but sometimes for the abbreviation, right? The model should be clever enough to understand this as well. So without, just by using this information, we can use this as a features and then feed into another deep learning or machine learning model, and then you will end up with a model by using these features apart from all the other features. As you might notice, like machine learning, deep learning, these are all being used interchangeably, right? But let me briefly explain. Machine learning is the roof term here. Machine learning is using data to building a predictive model using a data while finding the pattern within your data. And deep learning is just a sub, one of the methods and then the algorithms that we do machine learning. It is a way of building a neural network, using a neural networks to find this pattern. So that is the sub module of a machine learning. So as I mentioned before, we are going to circle around Spark NLP for healthcare library, which I am the part of it. So you shouldn't see this as a way of trying to explain the library. No, because this is the library that we are using every day to solve all these problems. So you may use other libraries as well. You don't need to stick, as long as you understand the concepts. Today I'm just trying to explain how we solve the problems using all these annotators, all these models. So as long as you have the same models and same concepts in another library, or you can write from scratch, or you can even use some pay-as-you-go services like AWS, Medical, Comprehend, etc. But these components, building one single pipeline and one library, putting everything in one pipeline is highly important when it comes to high compliance environments, because you are not able to pip install easily. We usually work in offline environment when we are working with the sensitive data. If we are lucky, of course, we have an internet connection, but most of the time, if we are playing with the sensitive information, you need to prepare the development environment beforehand. So that's why you need to make sure that you are sticking to the right tools. Otherwise, you may need to go back and forth, and then you may not get this permission easily from the like a system admins or the managers to take down the firewall and then pip install something or move some information and then take it out, like bring it up again. So this is highly time consuming and frustrating process. So that's why you need to make sure that you have everything you may need in your environment before starting the analysis. Okay. So Spark NLP for Healthcare is an extension of open source Spark NLP library. Open source Spark NLP library is already installed more than 30 million times. It is sitting on the shoulder of Spark itself, but everything that is running here can run on one single machine, because I'm going to run a Colab notebook today, which is going to run on 2 CPU, 12 gig machine on Colab instance. So which means that it doesn't have to be a cluster. If you are going to process large amount of data, of course, you may need cluster environment, but like 80% of the time so far, we didn't need this to solve certain problems, right? Because the scaling is usually the next step. But the first step is the building the pipeline and the devising this solution end to end without even using the big data, just using the data that we have, let's say a few hundred or few thousand samples, and then scaling can come afterwards. And it's not a big deal if you are using the right library. So everything that you see is fine tunable, modular. So the beauty of pipeline concept is like, this is the same pipeline that Spark has, by the way. As you can see, it's PySpark. So it is the same Spark library that you might see. This library can be used, by the way, in Java, R, Scala, and Python for different languages. The library itself is written in Scala, of course. Everything that you use on the Python side is just a wrapper. So the pipeline concept is important to build such a pipeline to answer all these questions that we have. Okay, so because now I'm going to move into the Colab notebook in a few minutes, but let me explain the pipeline concept at first. So pipeline concept is you build a pipeline. It's like a building blocks. It's like a Lego. You build a pipeline by picking some annotators, some modules from the shelf, and then connect the output of one module, like the output of sentence detector connected to a tokenizer as an input, which means that I ask tokenizer to take the input from sentence detection unit and then create a token. And then I send this token to normalizer to clean the token, etc. This is how I stitch everything together. So whenever a text data, let's say that I have one data frame with 1 million records, all the txt files in one cell, let's say, I can feed that text column into this pipeline, and this text will pass through each stage and a new column will generate it. You can discard all the other previous columns generated, because if you only need a word embed, let's say, maybe you are going to create some, build some classifier and you need an embeddings. Maybe at the end of the pipeline, you can discard everything and then you can just stick to the embeddings and then the document ID. So, which means that you can just save this as a Parquet, which is a columnar database, right? Like a data format that you can process in the other, like for other purposes. Maybe you are going to use the tokenizer steps or the sentence detection step for other purposes. We sometimes build a pipeline with 50 different stages without breaking the pipeline, because the less frequent you break your pipeline, the more flexible you will be to be able to process large amount of data, because you don't need to move your data, you don't need to swap the data within the memory, so that there will be no memory leakage. So that's why you should pay attention to accomplish everything in one pipeline if you can, because it's going to save you some trouble. So you remember this snapshot, right? This was the end goal. This was the higher goal. So to be able to end up with this, we usually use all these boxes. within the same library. Okay, as I said, you don't need to stick to this library. You can use any library. I'm here just to explain how we built such a pipeline to accomplish this. So we need the sentences, because documents is one large text, right? We need the sentences, and then the sentences needs to go to the tokens, and then the tokens, because the tokens are like tokens are like the minimal part of a text that we can assign some representation. Let's say, like everything starts from the token. Of course, different models use different tokens, like BB or some subtoken or some or white space delimited tokens, right? But everything starts with the token, and then we go up from token to the other annotator back again, because we use this token as an input to the relation extraction, as an input to the resolver, SNOMED resolver, as an input to the name identity recognition models. Okay, so these kind of art, these kind of like designing a diagram. We don't design like this, by the way. In real world, I never do this. I just start writing code, and then I just pick one output and then send as an input, and then take the output and then send as an input to another annotator, etc. And then I create one pipeline. Then we have some pre-trained pipelines, by the way, which you may not need to build such complex pipelines. Most of the time, you can just use one-liner pre-trained pipelines. For example, ADE pipeline, adverse drug event pipeline. If you use this, when you just one-liner .annotate or .predict, you will end up with tons of information, which is already coming from all these annotators. Within the library, it's possible. So first step, NER. Let's explain how NER algorithm works. So NER algorithm works is, so I'm just going to skip, like we have more than 100 NER models. But let me explain how NER algorithm works. I'm going to come back a little bit again, but let's explain NER, because we focus too much on NER, right? Name identity recognition. Of course, right now, for the last few years, the transformer architecture is ruling the domain, right? So you may not even need to worry about creating all these features. It's called Bertford token classification. But most of the time, because of lightweight solution and then the minimal difference between the accuracies, like by STM versus transformer BERT architectures, there is not much difference when it comes to NER. And understanding this is quite important. We call it BiLSTM CNN char architecture. It is it's coming from a paper released in the late 2015. So it's called BiLSTM char CNN architecture. So we create 3 features, actually 4 features, but in Spark NLP we use 3 features. The first feature is, we have, let's say patient is 67, okay? The first feature is embedding. You can use Elmo, you can use BERT embeddings, you can use word and glow embeddings as well, right? Word vector or glow embeddings. So you can use any word representation that is fine-tuned on a specific domain. Let's say that this is a healthcare domain, so you will probably have a domain-specific embeddings that you can use to generate the embeddings of your token. By using these embeddings, this is your first feature. Then the second feature is casing feature. Casing is because all lowercase, all uppercase, right? These are all important information, right? So if it's all uppercase, you might say that this is an abbreviation or some country names, or some, if it's starting with an uppercase and then go with the lowercase, you can say that, okay, there is some special term here going on, right? Especially in German and these kind of languages, even the uppercase ladder means different, because if all the names start with the uppercase over there, so you need to have a name like language specific models. By the way, Spark NLP can support more than 200 languages, but in the healthcare we are like more than 5 or 6 languages we support. So this is the second feature, casing feature. So we encode the casing features, all uppercase, all lowercase, this kind of 6 different variation, we encode this. And the third one is char features. Okay, this is important. Char features are making the model immune to typos. It's just trying to understand the pattern between the letters in your text. By doing this, even if you have a typo, so you don't need a spell checker, you may not need a spell checker to fix this. You can just, the model would, because the typos are minority, they are outliers, right, most of the time. And then the model will be probably smart enough to understand this typo, and then we'll just ignore this because if you have typo, if you are using word vector, not context not context aware embeddings, what happens? Because word to vec is just a dictionary, right? You get 0 embeddings over there, so you lose the major features because you have the embeddings feature, casing feature, chart features. If you have a wrong word out of vocabulary or some typo in your token, you will lose the embeddings. If you are using, of course, BERT embeddings, you will have the embeddings as well because it is using different tokenization, as you might know. It is and it's also context aware. So that's why if you get a wrong prediction within your text, maybe all your text is uppercase, and then the model is trained on a random text, which is uppercase and lowercase. We sometimes see this, like the customers ask us as, okay, I didn't get any entity from your model. We check this, and this is all uppercase. Okay, the embeddings is cased, so you need to pay attention. These kind of things. You need to apply some pre-processing to feed into the pre-trained models. So by using the same model and same text, just by applying pre-processing or post-processing, you can go up to like 30 to 40% different accuracy levels, or go up or down. Okay, I remember a real world project that just for the post-processing, because all the tools here, namely entity recognition, assertion, resolve, are just a tool, right? Just the steps that will make my life easier while solving that problem. But as a human, if I know the pattern, the decision maker's pattern, I can just follow their pattern. Maybe they are using some third-party lookup tables. I don't know. Maybe they are using some. Maybe they have some statistics for the most widely used drug names. Maybe if they don't let me know, if I try to catch all these drugs with the pre-trained models, why would I do this, right? It's like a beating the dead horse. Rather than doing this, if we talk to the decision makers a lot, by the way, during the problem, so that we try to understand why they call this, let's say that, like a patient entity, okay? Let's say that left upper quadrant paint on this right-hand side, okay? So what makes this problem entity? We need to ask them if the left or the body part should be included in the entity or not. Let's say that they are extracting there are some complex problems, by the way. Maybe they want to extract the name who signed the paper. But there are multiple names in the same document, right? Why am I just extracting John Smith? Maybe there are many other names inside the same document, but the use case only requires to find the name who signed the paper. In that case, you need to ask the decision maker, why do you select this? He will probably say that, okay, because it's the bottom of the paper, there is a date or sign here statements. So, okay, now you can use this kind of clues to isolate these names to make this name different than the other names. Otherwise, you need to annotate all the other names. Because if you are going to annotate something in CoNNL format, we call it CoNNL format, like a bioschema, which call it like the first token of the entity, John. The other tokens of the entity is like an I, we call it insight, like a person entity. So we have John Smith as a person entity. B and I is just showing the order. Okay. So that's why you need to ask tons of questions while annotating. Okay, then we feed this into BioLSTM network. We create this data set. We sometimes create a part of speech tag as well, if it's adjective or verb, etc. These are all important information to detect the tag of this word, right? We basically try to assign label per token. This is token classification problem. Then we feed this, and at the end of the day, we have a trained in-YAR model. So while doing this annotation, as I said, I'm not trying to teach you how to code. I'm trying to think like a healthcare NLP data scientist. So let's say that you are starting a project. There's a certain problem that you need to solve. As I explained before, maybe you want to understand what makes a metastasis spread from one organ to another, right? Or you want to find out who signed this form, who signed this discharge form. So it's an NLP and computer vision problem if it's coming from some, because you need the visual layout as well. So that's why we usually start with the annotation. There are different annotation tools out there. We have our own annotation lab, which is free, by the way. You can use it. Go ahead and use it for free, totally free. And you can use other annotation tool out there. There are some text annotation tools provided by the other libraries or open source projects. So what we do is, just by talking to annotators are the physicians, human physicians, by the way, which have some expertise in that domain. So most of the time we talk to them as a data scientist to explain how the model works. Because if they don't know how the model works, if they don't know how we tokenize, they probably may assign some weird labels. Let's say that EFGR mutated, there's a dash between EFGR and mutated, okay? Let's say that there's a dash here. Let me add a dash and then show again. So if annotator just select EFGR mutated as one phrase, this is one token, right? The tokenizer usually will if you don't customize your tokenizer steps, by the way, will just return this as one single token, because this yes, right? Then what happens right now? If this, yes, it is both, like both token belongs to the same entity, so it's okay. We might think it's okay, but if I see this, okay, what if there is no, and probably there is no embeddings for EFGR mutated. If I'm using glow embeddings, let's say, there will be 0 embeddings returned for this, because this is not a highly populated frequent term, right? EFGR or mutated should go alone to the embeddings so that they can get some embeddings rather than feeding this. So that's why we tell them, if this is happening, let us know so that we can customize the tokenizer as well. So that if we see some special characters between two tokens that are more important for the type of the entity, we sometimes go back and then change the tokenizer steps given the feedback that we get from annotators. Or we usually realize, like we usually notice this by doing some error analysis, by the way, because we train a model, then we get a prediction from the same training data. Why do I do this? For example, I have 100 documents. I split 80 to 20, and then 80 documents are annotated. Now, before testing on the test set, I get a prediction from the training set again to find because if these are shallow networks, right? If I train this further, it's probably going to learn a lot from the training set with this minimal data set. If I have just a small sample, I get a prediction from the same training set, so that I could understand maybe there are some label errors. If model fails over there, if model says disease, but the annotator says symptoms, I go and ask annotator again, are you sure? There are multiple annotators. We usually try to make sure that their agreement is high. We start with some seed documents at first, at the beginning of the project. And then we make sure that they live together, and live together means that they start to think together and in the same way, so that the model would learn from a stable mindset rather than a different variation. Otherwise, the model will try to generalize and then find a pattern with outliers, so which is not desirable, right? So that's why we try to increase the inter-annotator agreement, and then also try to make sure that their labels are correct. Of course, the model can be wrong if it says problem, but it's symptom, right? We ask annotator, we give annotators another chance to review this. We notice this by doing this. Most of them, half of the errors comes from annotator errors. They change their mind when they see this. They say, okay, this can also be done, because there is no one single truth over there. So if the model is wrong, of course, we try to understand why model failed over there. Maybe there are some conflicting entities. We check confusion metrics to find why the model is acting weird, right? Anyway, these are the process that we apply, and then we go back and forth between the annotators, and then we pay too much attention on the data set preparation. Just by changing how to prepare the data set, like this schema, like bioschema beginning inside and others, by the way, this data set, this table, just by checking this visually again and again, we fix so many errors to train a model before training a model, rather than trying to increase the data set, rather than trying to put some more money and time. If you just go back and then fix your co-NNL, most of the problems will be probably solved. That is what I have observed so far. So, as I said, we are using 3 main features. Sometimes part of speech is also used, but we are not using. So the tokens, so each token will have one label, right? The is the O means other, nothing, like negative samples. By the way, another concept here is that you always need to have negative labels. Whether it's a relation extraction or assertion or classification problem, you always need the negative samples, because you shouldn't just train the model to learn the label. Also make the model learn from negative samples as well. Negative means that if you are training, let's say, the cancer patient, if let's say you are trying to detect one entity, like adverse drug event entity. So you need to give the model some negative samples. So otherwise the model should understand black and white, right? Or maybe you have 5 labels. So you need to have the 6th label as a negative sample. Negative sample means that the model needs to assign some colors to each entity, each token. Color means that some pattern, find some boundaries between the entities. That's why you always need one more class. Actually, I don't even need to say that this is the foundation of the machine learning. Of course, you need to have some other classes to separate the target classes. So what we do is we try to feed these features extracted from each token to a network, and then ask model to assign a label. It says O to O, okay, this is a perfect classification, and then the O to company, so it tries to go back during backpropagation and reduce the error, right? Okay, so NER is done. Now we can go back to notebook. Where is this notebooks, by the way? So let me just go back and then show the notebook. So where did I get this right? So I can just show. I hope you still see my tab. So I am right now in a GitHub repo, which is called Spark NLP workshop. We are going to share all these links under the video on YouTube, by the way. So there is a certification training healthcare folder. There are more than 50 different notebooks here. What I'm going to do is go back tutorials. This is 1 hour session. So we prepared the notebook just for this one. It's called 1 hour notebook, Spark NLP for healthcare. So right now, this is a big notebook, right? It may not be loaded into GitHub. You see, it took longer. So because each notebook, we have an opening collab button, but I usually apply this trick here. If you are looking at my address bar right now, just before the .com, you can write to collab, and then it's going to open up in collab. Okay. So if you are not able to open any notebook, Jupyter notebook in GitHub, you can just apply this trick. Anyway, now this is open in the collab, so I can just connect to a collab instance. And you don't have the license right now. You can just apply to license later on if you wanna test this on your end for free. There are like two weeks valid license, so you can go to johnsonalves.com, install, and then sign up, and then fill the form, and you will get a free trial, which you will end up with some JSON file. So let's start this session. Okay, I'm not going to run all the notebook, but I'm just going to show you how to prepare your environment. I'm just going to run this first cell. First cell is just asking me to upload the JSON file, and then writing into an environment. And now I'm just going to install everything by using that JSON. I'm not using my keyboard right now, right? Because everything comes within the JSON file that you are going to get when you subscribe. Over there is a trial license. If you are academic, it's completely free, by the way. There's no trial. You can just use as an academic purposes for free for a long time. There's an active Slack channel. You can also go ahead and check Spark NLP Slack channel, which we usually answer within 1 hour. Okay. So there are, as I said, like 30 million downloads in open source NLP, but healthcare NLP, we don't know the statistics. Why? Because it's the license. There's no pip install. It's a pip install from the secret key that you get from the JSON. But we know that for the last 1 year, like 2 million times this pre-trained models used, because there are more than 600 clinical pre-trained models out there that you can use. Anyway, so I'm not going to write a code, but I'm just going to show the starting the session. Now everything is ready. How NER works, right? So these are all the NER models that you can use at one single line, okay? And there is one giant model that is extracting 80 plus entities at once, like the injury or poisoning, or rather than saying problem entity or clinical findings, you have more granularity if you pick this model, because you have a kidney disease as a separate entity, and you have, you have a kidney disease as another entity, and you have, let's say, hypertension as another entity, heart disease as another entity, rather than having only one entity for all the clinical findings. So how we build the pipeline here? Building the pipeline is, in Spark NLP, everything starts with the document assembler. We feed a token, like we feed the text itself. And from now on, we pick all the models one by one from the library. Okay, now, because I'm going to do named entity recognition right now, I know that named entity recognition is a text class, is a token classification problem. So I need the tokens. And then to be able to get the tokens, I need the sentences, because I know that named entity recognition models are usually trained with the sentences. There are some pre-trained sentence detector model that is specifically trained for splitting the sentences in the healthcare data. Okay, so I take the document column, like I feed the text column as a DF. Let's say I have one DF data frame. I feed this text column and then end up with a document. Now I'm going to use this column to stitch everything together. So document will become sentence. Then sentence as an input will become token in the tokenizer stage. And then sentence and token will become input to the word embeddings. Now I'm going to have the embeddings per token. Now I created one feature. All the other features will be calculated within the same model. So I don't need to worry about the casing feature, chart features, because that is what is being done by a medical NER model. Okay, as I said, you can use other NER models, other libraries to do the same, but of course the notation will be different. So I say that use NER GSL model. NER GSL is our flagship NER model, which is 80 plus entities at once. If you have that JSON, that trial license, you will be able to access this model. You will just load this and then feed the column that is generated already, sentence, token, and embeddings, and return the entity, like NER entity, BNI text. And then you use NER converter to get rid of BNI, like a John and Smith becomes John Smith. Okay, or let's say diabetes mellitus. So rather than have B and I insulin, you will have B and I diabetes entity. You will have one entity, diabetes mellitus entity. Okay. And then you feed the pipeline. Now, after you're fitting this, you have one pipeline from now on that you can use everywhere. It's like when you have this, after fitting, you can save this. It's like an scalar, right? So when you fit the pipeline, you can save it, you can pickle it, and then you can use it anywhere that you want. You can move it to somewhere without dealing more about how to build the same pipeline again and again. Okay, so let's download some sample text. You can just download this sample text from our repo. We use MT samples website to extract some data, some open source data, and I create a data frame. So this is a data frame. Okay, I have just a text column, and then like let's just do this maybe, and then I just created the data frame right now. I downloaded and I created the data frame. Now this is one sample. As you can see, this is one clinical text. So now I'm going to extract entities from this text. So as a clinical report, so this could be, header information. This could be header. There are some clinical conditions here. Let's see what my model would return, right? When I transform this, my model will return this, like with the same pipeline. Like a sample gets O label. So hematology gets clinical department label. Discharge summary gets, it says there's a discharge admission entity. So mesothelioma is an oncological entity. Description is a section header. By using just this information, I can even split my document into different sections. And then I can just exclude the entities falling under history section. We have a sentence chunk splitter annotator as well. We have sentence detector annotator as well. By the way, there are some demos apps in John Snow Labs website that you can go ahead and then check all these models. So if I just go to Spark NLP in action, like demo.johnsnowlabs, I can just go ahead and then check all these models without writing any code, just to see how it looks. Okay, there are some sample text. These are all offline streaming apps that you can see how they look like. Okay, so that you can understand which NER model does better or extract what. Coming back to the original notebook, now by getting the statistics, I see that I have like 29 gender entity, 26 symptom entity, etc. Okay, for 10 documents, by the way. These are all 10 documents. Now I can, by using the converter, NER converter, we call it, rather than BNI, we create the chunks right now. So I can just write the chunks. So that like hematology is clinical department entity, and pleural effusion is a DZM syndrome disorder entity. Atrial fibrillation is heart disease entity, etc. You see, now I have the meaningful chunks from the text. Now I can use this information. I can even sort the patients, or just by using name identity recognition model, I can just write this to some Elasticsearch or some DB, right? And then I can just find all the patients having these terms, rather than just writing pages of regex codes. I can just give me all the patients who had a heart disease populated text documents, right? You can even inject this into your workflow right away, just by using NER without writing any single line of code. As you see, I didn't write anything. You will just point to a folder, text folder, and then read all the text data. Or you don't even need to create a data frame. Let's say we have a way of doing this. We call it light pipeline, because in Spark is designed for big data, right? But when it comes to small data, there's some overhead that you may need to suffer. But to get over this, we created light pipeline concept. Or the light pipeline, there are some blog posts, by the way. If you just Google my name and Spark NLP and light pipeline, you will see tons of articles that we try to explain. For example, there's a specific blog post at Medium explaining light pipeline concept. So rather than dealing with the data frame, what if you are going to deploy a REST API with a fast API, right? And then you want to your user will upload some text file or type something, and then you will return some results without going over all this building the pipeline or input output columns or data frame. You don't need to do this in light pipeline. Most of the time, like this is like maybe 90% of the time I use light pipeline, by the way. So you just feed a text or list of text, list of string, and it returns everything as a Python dictionary. Okay, so to prettify this, there are some way of doing this. It's just look through, zipping, etc. Right? Let's say I feed this, and I end up with after one line of prediction, which means that this light model is already generated. So you can do this and then pull it from your disk later on. Okay, so that no one needs to understand or no one needs to deal with how you build such a pipeline. So this light pipeline might be combination of 50 different stages, like a grief complex. Like I remember using 46 different name identity recognition model in one project, because I need to extract different entities given the type of the document. So I had to use different NER models given the type of the documents. Okay, so you can have a giant ugly pipeline here, but when you fit it, you save it, and then from now on you can use as one-liner. We call this pre-trained pipelines. So you can feed the text, and then you end up with all this information. You see, so for example, these are representing the word embedding stage. It's like, let's see if there is any out of vocabulary. Looks like our embeddings is really good. There is no out of vocabulary. If there is, it is going to reduce to, as you know, it's going to reduce the probability of having that embeddings, and then the model will be weaker, but looks like it is doing good. But even if it doesn't, there are other features to make up for the out of. You see, just one-liner is going to return all these information, like the borders of the token, embeddings, and then the named entities and their full and token versions. So I can just loop through and then end up with this table. So which means that your API, you can just fit this text and then end up with this table. To make the life easier, actually, I remember doing, let me show you, in the workshop repo, I have one notebook at the bottom. It's called Inert Playground, Streamlit app. You can just quickly try this. It is going to run a Streamlit app on the collab by using ngrok. Ngrok is going to let you expose your endpoint so that you can share with anyone. So without using your own computer, you can deploy a Spark NLP for healthcare API or app like this. Okay, so this is the app. This is the snapshot I got from that app. It's going to deploy 5 to 6 different NER model. So you would be able to write something, type something, and then end up with this kind of visualization. You will see all the NER on the left-hand side. You can check or uncheck or merge, and then you can, yeah, it's really fun, by the way. You can just plug and play any NER model because we have more than 100 NER model, right? You can just use any of them and then use this notebook. This notebook is designed to let you start the same Streamlit app on your local or on collab. Okay, so this is the NER. So we have a visualizer so that you would be able to understand, you will be able to visualize the entities with different colors and entity names. Okay, just with one text. Okay, so you end up with less than a second, you will end up with this kind of predictions. Okay, live pipeline is much faster. So we right now covered NER pipeline. Let's go back to the slides. Maybe before going to the slides, maybe I can try to check if there's any question that I can answer. Actually, let's do this after the session. We will have enough time to do this. We will have enough time because to answer, if I start answering the question, I need to jump back and forth, which would be a lot of distraction for everyone. So assertion status, next one. We covered name identity recognition, which is the first module of clinical NLP pipeline. The second one is assertion status. Assertion status is basically finding the negativity scope given the context. So let's say lung cancer. Lung cancer is an oncology entity. Now I want to find if this is negative, positive to family members or some event that is going to happen in the future, right? So for example, here, mother with lung cancer. So the patient has no lung cancer right now. You remember I gave an example that give all the patient have a diabetic history, etc. But if you don't check the assertion status, you might pick these kind of entities, which is not related to patient, but the patient's family members. So you would be mistakenly pick that patient as a lung cancer patient. This is highly important for clinical trial recruitment process, because in the clinical trial process, you invite some patients to do some real world evidence, right? So to collect some real world evidence, and then you have some inclusion and exclusion criteria. You say that, okay, let's invite the patient who have a lung cancer and also recurrence status is positive, and then also metastasis on the right lung. Okay, so for this patient, if you just use regex and then invite this patient, you are wrong, because this patient is a breast cancer patient, not a lung cancer patient, because you just picked the entities, but you didn't check its assertion status. Or you say that, okay, the patient will need a head CT tomorrow. Then if you want to query this, give me all the patients who had a head CT, you could be mistakenly select that patient, because this patient didn't have a head CT yet. It will happen tomorrow. So the assertion status, as a human, when you read this, you understand the concept. So if you look left and right, we have some window scope, we call it, like 9 token left, 15 token right, or the other way around. You can also customize this in Spark NLP. And then you will be able to find the assertion. So this is a pre-trained model, by the way. Like, for example, the patient went under chemo for 6 months. So the patient is not under chemo right now, chemotherapy, right? So when you check the assertion status, give me all the patients who are going under chemotherapy right now. You would mistakenly pick this patient, which is not correct. So that's why assertion status is adding one layer of knowledge when you are working with the clinical entities. So we have some metrics. Let's not worry about this. And then I explain how to do this, checking to like a 9 token left, 15 token right, because the statistics say that 95% of the tokens fall in this scope. So you can also customize this. This is the chunk classification problem this time, right? We have the chunk. Now we try to find its scope label. Maybe it's like a aspect-based sentiment analysis, right? We went to a restaurant, the service was good, the dish was terrible. So what's the sentiment of this sentence right now? Right? Given the entity, you have different sentiments. Service was good, service was positive. Dish, like the main course, right, was terrible. So which means that we have two sentiment given the entities. So the same appears with assertion and NER. It's kind of aspect-based chunk labeling. Okay, so there are different assertion models given the concepts. So if you are dealing with a radiology, maybe you are reading a radiology report, you find the confirmed and suspected entities. You can go back and forth between the entities, and then as a physician, as a radiologist, you can say, okay, the right lung shows some nodules, may have some nodules, right? So this kind of suspected or negative or confirmed. So you may need, so you can use these models and NER models to build some radiology report understanding pipeline. Okay, so let's go and to the notebook and let's see how this works. We just explained assertion status, right? Before going to assertion, I noticed that there is a chunk merger. Chunk merger means that, let's say you want to use 10 different name identity recognition models in the same pipeline. You can merge all of this together without overlapping by using some rules, like which one to override to others. There are some rules over there. You can whitelist, blacklist. You maybe one entity from one NER model is better than another model, because one NER model might doing really well when it comes to oncology entities, but another NER would be doing really well on data entities. Maybe open source model can also do very well on the name entities, right? So you may want to merge this, but also try to close one of their eyes. We call it whitelisting or blacklist, so that the model doesn't try to assign some labels to the entities that are already weak. There's so much flexibility that you can play with this pipeline, and then you can fit 3 different NER model or maybe 10 different NER model into the same pipeline. Okay, now we were talking about the assertion status. You can check the same notebook for training as well, how to train a new NER model from scratch. Okay, it is as easy as I said, as long as you have a data set, you don't even need to write anything else. You will just run this notebook and then you will be good to go. So let's assertion status. So let's click on this and then assertion status. Assertion status is, as I explained in the slides, so it is depending on the name identity recognition model that you are going to use. So you need to feed the NER chunk as an input to assertion. Till here, everything was same that we use for NER, right? Till here, we have everything that we need. Now I have the NER chunk. Now I'm going to use this as an input to an assertion DL model, and then it's going to assign a label. I can even filter later on, do not return the entities that are present or that are family members, okay? Then I feed the pipeline, and then I will be able to, like feed this sentence, this text, and then end up with these entities. Severe fever problem is a present entity. Stomach pain is an absent entity. Let's see stomach pain. So he shows no stomach pain. You see, he shows no stomach pain. So it's an absent. Short of breath, conditional. What does it mean, conditional? Because he also becomes short of breath with climbing a flight of stairs. So it only happens when he tries to climb stairs, right? So it's a conditional. So it's not happening all the time. or father with Alzheimer, right? So father with Alzheimer. So it's family member associated with someone else, it's called. Okay, by using this, now I have the pipeline like this one. So you can visualize this entity and assertion as another label. Okay, so you can have this kind of nice visualization and app on your in your dev, right? So there is another concept, we call it contextual process, because when it comes to healthcare NLP, you may not need to train any model actually. Let's say that because we have seen that a lot. That's why we developed this annotation.
Basil, I'm sorry to interrupt. Actually, I guess we are running short on time. So now we can take a few questions and then we can wrap up the session.
Okay, then. So let's take a questions then. So yes, we have 10 minutes. How much labeling effort went into, let's open up the slides. How much labeling effort went into leveraging this data? Was it general labeling or goal specific? This is the first question. So labeling effort, we usually try to make sure that at least 50 entities per class goes into the annotation. So as long as I have, let's say that I have 3 entities to predict problem, test, treatment. So whenever I catch that 50 entities per class, maybe I will get this number in 100 documents, right? Or 200 documents. But most of the time, all the models that you see in the library is at least 500 documents. And in real world project, we usually aim to annotate 500 documents, 500 text document, like 500, and usually 400 tokens per document. Another question, clinical data will be converted to the vectors using TF-IDF or embeddings. No, it's an embeddings. So it's a pre-trained embeddings. It could be word embeddings like a globe. It could be fast text embeddings. It could be BERT embeddings, ALMA embeddings, X-large embedding, Distilbert embeddings. So this is the embedding stage. We support all the transformers, by the way, that you can. So in production, another question, in production, how will this be tested for unseen data? So what we usually do, as I explained before, we split that 20 to 30% at the beginning as a representation of the real world data set, because we pick the training data set as a representation from the real world data set as well. And then we start annotating and then test on the test set. Of course, after a few months, we usually do not close the projects right away. After a few months, we collect some feedbacks from the customers and then the projects, and then like the hospital or the product that is shipped into the production, right? So we gather some feedbacks. We do some error analysis. We annotate or fix the pipeline, because you may not need to annotate all the time. Maybe sometimes adding some keywords. That's why I was going to explain contextual parser. You can add some entities. You can use your own lookup list to make up the deficiency of the trained model. In healthcare, believe me, you will the rules still rule if you have some domain-specific rules. Another question, how NER deals with grammar mistakes in clinical text? If you have 500 documents, and then the typos and then the grammar mistakes will be less given the majority, right? Most of the time, these kind of errors are minority. And then the machine learning is all about generalization, right? So if you have noise in your data, like 5 to 10%, the model will will probably skip them. But given this, depending on the algorithm that you use, like the algorithm that we use, even in the transformer architecture, they are right now good enough to ignore this kind of typos. So even if you have a typos, for example, because if you have typos, you will not have any embeddings in globe, right? But in BERT, you will have it. And then the char features, character features will help you skip that spell checking. If this fails, if you are still worrying about the typos, there is a clinical spell checker models, pre-trained models. We have a drug spell checker, for example, which we trained from entire corpora. And now we will be able to fix the typos in the drug. It's like a classic Norway approach, right? Another one, how do you differentiate between multiple instances of some type of entities? Like sometimes it is record date, sometimes discharge dates. Yeah, this is a good question, by the way. As I said, since this is a sequential, so if there is a date which needs to be labeled as a record date, if you get that clue from the same sentence, since these are sentence-based, you are lucky. If not, if the date is just, one header, let's say record date, and another one is just the date. So these are two sentences right now. Let's say that your sentence splitter failed. Now you have a problem, because if you train with the sentences, the model is not seeing the header information. In that case, you have a problem. So that's why if I see this, I sometimes train with docwise rather than, so I just skip the sentence. Or there are some visual, if the visual information is so important, let's say that this is a chart. So I can use OCR, Spark OCR, or some layout LM algorithm, right, to extract the entities. So there are some visual NER models that is extracting key and value pairs. So because if I see the record date and then the date, and then the discharge date and a date, what makes this discharge date? This chunk on the left-hand side, right? Because the embeddings of this is also going into the model, and this is a sequential model. Now I can understand. The model is able to differentiate this date from the other date. Let me select some random questions because there are many which I will not be able to answer. Will the clinical data be converted to the vector? Wait, this is the same question. Yes, another challenge is doctors may use abbreviations when writing clinical notes. Yes. So this method will work when the medical prescription data is not same format, like different structures. Yes, because if you are talking about the medication extraction, we just don't extract this label prescription data. We add some other Twitter data, other drug bank data, some official PubMed articles, etc., to increase the coverage. And then it is usually when it comes to pathology, the numbers are, by the way, the accuracies are really high, above 96, 97. But for the other specific, let's say that you are only working with the breast cancer patients, so you need to find this kind of specific case studies and notes to annotate further. Otherwise, these are rare cases, right? So someone asked, can I explain about the negative class? So let's talk about the relationship extraction. It's a perfect example for the negative class. Let's say that I want to find the relationship between the drug names and advertisements. So while annotating right now, we ask annotator to annotate the drug and ADE, let's say that rash and Advil, okay, one drug and one adverse event. We ask them if, as a human, when they read, there is a relationship or not. They say, okay, there is a relationship. We ask them, okay, annotate. If there is no relationship, what they do? We tell them skip, okay? Because we create this as a negative sample, no relation. Because we want the annotation effort to be as fast as possible. If we have time, we ask them label this as a negative relation. If they don't do this, I can create negative labels easily, right? Programmatically, I can still create so that I can save so much time. So negative class, if the model only learns in terms of machine learning perspective, if I train with one label, relation, positive relation label, the model also needs to see non-relations, right? Like the drugs and adverse events within the sentence, but there is no relationship maybe. It's coming from somewhere else, right? In that case, the model also needs to know how to say no, just like how to say yes. Another question, transformer like BERT is more effective in NER than LSTM? Yes, by the way, yes. Always BERT for token classification is always higher in terms of accuracy. Most of the time, according to the model so far I trained, most of the time it's higher, but it's too expensive, right? Right now, I am able to, by using LSTM, I can use 50 different NER models within the same pipeline. But in BERT, if I use BERT-based NER models, each one of them is 350 megabyte. So I cannot use more than a few. It could explode my memory. So that's why there is the difference, accuracy difference is not that much, by the way. It is usually a few percent. So in production, you wouldn't even notice this. Usually, but if you have one giant NER model, you don't need to use any other NER models. You can use the BERT version, BERT for token classification approach, and then you would be happy. But the prediction will again be a little bit slower. But if you use distill BERT, it's fine, right? So yes, but I would suggest using the LSTM version. So boosted knowledge graphs. Yes, often NER is boosted with knowledge graphs. We actually boost the knowledge graph with NER, the other way around. So we build a knowledge graph with NER, or you have the NER model and you have some static knowledge graph. You can use knowledge graph to make up the deficiencies of NER if you have some terminologies already written into a graph. So we can right now in Spark NLP, you can create a 1DF with the pipeline and then send it to the Neo4j right now. In NER, how can we feed long sentences for training? BERT only has 512 tokens. Yes, nice question as well. So you don't need to use BERT over there. As I said, you can feed any like sentence if you are using Glow or word embeddings approach. As I said, the accuracies are not that matter here or there. But if you still want to use the BERT version, you may want to do some sub-sentence splitting with the phrases by using the boundaries, or you can use long former, but long former has no token classification. But we are talking about the sentences and 512 tokens. 512 tokens, it is a document, right? So the chances are really low that you will have more than 500 tokens in one sentence. So you don't even need to worry about this. So Spark NLP, there is an open source version. Another question is about if it's general purpose or health. There is an open source version Spark NLP which everyone can use. There are supporting 200 languages, pre-trained models, tons of pre-trained models. Healthcare extension is just healthcare. We are going to have a finance and legal extensions in October as well. So let's say the library that I explained today is health specific. For the academic research, you can just get you can go here and then sign up, or there is you can email info@johnsonowlers.com and then ask for you are a researcher. This is your university email. You can ask for a free trial without limits. So if you want to learn more about this, let's end the session like this. If you want to learn about this, you can go to so let's go to the workshop, right? So in the Spark NLP workshop, open source, this repo, you can go to tutorials, you can go to certification trainings, you can go to healthcare. There are 50 different notebooks here. We have some papers with code rankings as well. We have papers as well. So you can check Medium, Spark NLP Medium page, Johnson Knowles YouTube channel, webinars, tons of notebooks, tons of workshops. You can just Google my name and then on Google you will find tons of all these kind of similar sessions you can find over there. And is there any? Looks like we are fine. Thank you for joining me today.
Thanks a lot, Vessel. On behalf of Analytics Vidhya, I would like to thank you for devoting your time and have delivered such a wonderful session with a great content. And I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future.
Thank you. Thank you. It's my pleasure. Thanks for inviting me.
Yes, sir. Thank you so much. And before we wrap up the session, I would like to request all the attendees to please engage in the feedback poll so that we can conduct such more sessions with you. Here is the poll.
There's a feedback poll. Yes. For the handwritten recognition or table extraction, there's a Spark OCR library as well. You can check its own workshop repo, or just Google Spark OCR. You will find tons of information if you are dealing with extracting information from PDF and images and then feeding into the NLP pipeline, including the healthcare, like handwritten detection or signature detection. Okay, you can use that as well. So we also have comparison with the other libraries, Core NLP, Stanza, SciSpicy, Hugging Face. You can also check our blog posts. We even have one blog post to cover AWS, GCP, and Azure comparison. You can find it.
Okay, so I can find a good feedback here. And so everyone, we will wrap up the session here. Thank you so much, sir, for delivering such a session. And we will be back with another session of the DataHour tomorrow, 28th July, which is on computer vision landscape from 7 to 8 p.m. In the chat section, there is the link. Till then, bye-bye and keep learning, everyone.
Thank you. Bye-bye.
Thank you, sir.
Yeah.